In this lecture we'll talk about probability. Now since a probability and statistics class is required for this course, hopefully most of the material in this lecture is simply a refresher. Now computing past returns is pretty easy, as we saw in the last lecture, and this is because historical prices are known. But the same is not true about future returns. The issue is that we don't know what future prices are going to be, and we need to know future prices in order to compute future returns. So what we end up doing is we make probabilistic statements about possible values of prices and returns in the future. And this is why we need probability for much of investment and finance. So let's start with the underpinnings. Let's lay the groundwork. A random variable, well, suppose a random variable x, which I'll always denote by a capital value, a capital letter that is, can take values little x in some set, and this will be a calligraphic x. So the little values will always be the values that the random variable can take. And I'm simply using this calligraphic notation to denote a set. Now if that set happens to be countable, we will call x a discrete random variable. What do I mean by countable? I mean if I can take the number of elements, or if I can take the elements of x and just count them in sequence, then it will be countable. So a set of a finite number of things, let's say that calligraphic x, my set, has 10 things in it, then I can count those things and it is a countable set. And if x can only take the values, those 10 possible values, then it is a discrete random variable. It turns out that the set doesn't actually have to be finite in order to be countable, but this is somewhat semantic, so that if the set took the values of the integers 1, 2, 3, and so on up to infinity, x would still be a discrete random variable. So if x is a discrete random variable, we use the notation p of little x, which would be any little value inside of that set. And that notation denotes the probability of x, the random variable, taking on this little value x. And we call it the probability mass function. Now let's say x is a continuous random variable, so that the set is not countable. An example of an uncountable set would be the interval between 0 and 1. It turns out not only are there an infinite number of things inside of the interval, but there's such an infinity that I can't even count them. So if x is a continuous random variable, we have an alternate notation for the probability of some little value, x. And we use the function f instead of p, and we call it the probability density function. We'll think of this f of x as exactly the same type of thing as the p of x. That is, we'll think of it as the probability that random variable x takes on this little value. In reality, the semantics of it are that with a continuous random variable, there's a 0 probability of x taking on this little value x. But as I said, we'll think of this f of x as being the probability of taking that value. Now for discrete random variables, we have a couple of important properties. First, the probability mass function must always be must always be 0 or greater, non-negative. Also, if you sum over all possible values that the random variable can take, if you sum all the values of the probability mass function, you should find the value 1. That's saying that the sum of all probability is always equal to 1, or certainty. So that if you are trying to compute the probability that the random variable takes any value, well, you know that must be certain that it takes at least some value, and that's equal to 1. For continuous random variables, we have an analogous set of properties. First, that the probability density function must be non-negative for all values in the set. In this notation, the upside down A means for all. And then instead of summing, we take the integral over this probability density function. But this is essentially the same thing as a sum. With the integral, we're just summing in an infinitesimal way underneath the probability density function. And so this integral here is summing all of the values of the probability density function. And it has an equivalent interpretation, that the sum over all possible values that x can take of its probabilities will yield certainty. So if x has this continuous distribution that looks something like a normal distribution, let's say, then what we're doing when we integrate is we're literally taking dx widths, just these infinitesimal widths, and the integral is just adding them up together, where f of x is the height of this function. So we're taking each f of x height and adding it to the next one. And we're doing this in an infinitesimal way, so that there's so many of them that we actually can't even count them. And that is exactly what an integral does. It integrates under that distribution or that function. And so the integral, if you were to take the integral under the whole density of any continuous random variable, should equal 1. Now, expected value is a very important concept in probability. For a discrete random variable, we define the expected value as the probability weighted sum of all possible values that x can take. Now recall, let's say that x, the set, can take n values here. And then a simple average would simply be x times 1 over n. And we could pull the 1 over n out of the summation. And we would sum over all of the values in the set. There would be n values. But what we're doing here is, instead of just weighting them equally with this 1 over n, we're actually substituting probability weights, some of which are greater and some of which are smaller, for differing values of the x. Now, for a continuous random variable, we have an analogous definition, but instead of a summation term, we have an integral. But essentially, what the integral is doing is exactly the same thing as I mentioned in the previous slide. It's simply taking the probability and it's weighting the value that the random variable can take. And then we're just doing this infinitesimal sum. The notation for expected value then is e of the random variable x, whether or not it's discrete or continuous. Now let's look at some properties of expectation. Suppose we have two potentially different random variables, x and y, and then we have two constants, a and b, that take values in, that's what this notation means, the real line. So the real line, that notation r, just means any value between negative infinity and infinity. Literally, not only any integer on that line, but any decimal, any fraction, anything between any integers. So any real valued number is what this notation means. So given that we have these two random variables and we have some constants, so these constants a and b should look something like 72.3 or 5.7. The expected value of ax plus b, it turns out, that is equal to a times the expected value plus b. So that is one important property of expected value is we can take it through the summation term, so the expected value can be distributed across the summation, and then the expected value of the constant b is b, and any scaling constant of a random variable can be pulled out of an expectation. We'll prove this on the next slide. The next important property is that the expected value of the sum of two random variables, that is the sum of their separate expectations. Again, that same distributive property, we can just distribute the expectation through. So it turns out that the expectation is not interpreted as the value that the random variable takes. In fact, the value that it takes can be one of many potential values. But in expectation, that is, if we were able to draw many, many values of the random variable and observe what values they take, we would expect that an average of those many values would get close to this true value, expected value of x. And that's essentially what I'm saying here, that if we observed many realizations and took an average, we would expect to get a value very similar to this one. So now let's prove those properties of expectation. We can use either a discrete random variable or a continuous random variable notation. That is, we can use a summation or an integral. I'm going to do it with an integral, but we can substitute out later a summation notation instead. So we begin with the expected value of ax plus b. Now by definition, according to the integral notation, that is equal to the integral over all possible values that x can take of a capital X. I'll put little bars on my x's, my capitals, so that you can differentiate those, plus b. And now we have to take a probability weighted version of this. So we multiply each, and I'm sorry, this should now be a little x, because once we are summing or integrating over possible values, we're actually using little x's, whereas inside the expectation notation, that is a capital value, since it's still a random variable inside that notation. Now the next step of the proof is simply to distribute the integral. If you remember from calculus, you can rewrite that integral as the summation of two different integrals. So let's write that's equal to the integral over all possible values of ax f of x dx plus the integral of b f of x dx. And now since a and b are just constants, we can rewrite this as a integral x f of x dx plus b integral f of x dx. And now what do we notice? Remember, one of the properties of probability density functions is that if you integrate over all possible values, that should just be equal to 1. So we have b times 1 here. And then our definition of expectation is just that. That's a d. It's just x the integral over all possible values of x weighted by its probability density function. So what we have is a times the expected value. And so by definition we write the final step, a times the expected value of x plus b times 1, or just b. So that's the end of the proof. We could likewise prove the expected value of x plus b, but I think that you can see it exactly how you would walk through the same steps, simply first beginning with the definition, and then distributing the integral through, and then finalizing with a definition. So I'll leave that for you to do on your own. Now let's talk about the variance. So generally speaking, for discrete or continuous random variable, it doesn't matter, the variance of the random variable is defined as the expectation of deviations of the random variable from its expectation squared. So in particular, if x is discrete, what does that formula look like? Well, it looks like the summation. So now recall, we are actually taking the expected value of that quantity. So we need to take the probability weighted sum of that quantity. If x is continuous, we're going to do the probability weighted integral of that quantity. And now it's important to distinguish that once we shouldn't be bothered by the fact that we see the expectation notation appearing twice. That just means that there are two integrals or two summations. But what we really want to do is think of this first expectation now as just a number. It's no longer a random variable. Once we've computed the expectation of x, so to compute the variance, we would first compute the expectation of x, and then we could actually refer to it as expected value of x. We could give it a name like mu, the Greek letter. And that is simply a number now. It's simply something like 17.5. It's no longer random. In fact, what we say is, because expectation is an integral or a summation, we say we've integrated out all of the randomness of the random variable, and now that is just a number. So here, in the definition of variance, what we really have is expected value of x minus mu, and that's a capital, squared. And this should help you visualize the fact that this mu here is just a constant. And the expectation then is taking a probability weighted sum or integral of deviations of the random variable from that value, mu. And it's actually the probability weighted sum of those deviations squared. Now, using the properties of expectation, we can show this result, which is actually a very convenient way to compute variances. In fact, you'll see much later as we continue to use expectations and variances that in the case that you need to compute a variance of a random variable, it's much easier to use this formulation than the one on the previous slide. So let's prove how we can arrive at this formulation. Starting with the definition on the previous slide of what variance is. It is the expectation, and I'm going to substitute the mu notation for the expected value here of x. It's the expected value of squared deviations from the mean. And why do we square the deviations? If we didn't square the deviations, then values of the random variable below the mean would counteract values of the random variable above the mean, and they would essentially cancel each other out and not give a measure of dispersion. So for a symmetric distribution, like a normal random variable, you would find that if you just took the expected value of deviations from the mean, you would get to 0, and that wouldn't give you a proper measure of dispersion. So what we do is we square. Another method would be to take the absolute value of the deviations. It's just that squaring the deviations allows us to take derivatives and so on, and that allows for easier computation. But taking the absolute value as well would give a measure of dispersion around the mean. So to continue with the proof, well, what is that by definition? We can expand the term under the expectation as expectation of x squared minus 2 mu x plus mu squared. All we've done is expanded the inner quadratic. And now from the properties of expectation that we studied before, we know that we can carry the expectation through each of the terms of the summation. So that's equal to expected value of x squared plus expected value of negative 2 mu x plus expected value of mu squared. Now mu squared, that is a constant, so we don't need that expectation there. And here, in the second term, we've got a constant that is negative 2 mu scaling the random variable. So we can pull that out of the expectation. And we write that line as expected value of x squared minus 2 mu expected value of x plus mu squared. But note that the expected value of x is mu. And so that equals expected value of x squared minus 2 mu squared plus mu squared. Now this term cancels that term, and what we have is the expected value of x squared minus 2 mu squared. And mu being that, we've now arrived at the exact definition of the variance. Now the standard deviation is simply the square root of the variance. The standard deviation is nice as a measure of dispersion because it actually has the same units as the random variable x, whereas the variance comes in units squared. So for example, if I were using the random variable height of 10-year-old boys in the United States, then the variance, I could first compute the mean of all 10-year-old boys, and then I could take the probability weighted sum of the deviations of each boy from the mean to compute the variance. But by squaring the values, so if I took each boy and subtracted off the mean and squared the value, I would no longer be dealing with inches or centimeters, but I would be dealing with inches or centimeters squared, so that the variance would end up being a quantity of of inches or centimeters squared. But by taking the square root of the variance, then I would be back to the units of inches or centimeters. And that's directly comparable to the random variable itself, which is why standard deviation is a very nice measure of dispersion, because it comes in the same units as the random variable. Now let's talk about covariance. If we have two random variables, x and y, then we define their covariance as the expectation of the product of their deviations from their means. So we take deviations of x from its mean, deviations of y from its mean, and we take the expected value of that product of deviations. Note that by definition, if you were just to substitute an x here for y so that you had the covariance of x with itself, that you would end up with just squaring that, which is the definition of variance. So just as you would intuitively think, the covariance of a random variable with itself is just the variance. Generally speaking, the covariance is measuring the tendency for these random variables to co-move, so that if when the deviations of x from its mean are large, if the deviations of y are also large, then these random variables co-move in a positive way. However, if when x is deviating in a large way from its mean, y is not deviating in a large way from its mean, then these random variables actually co-move in a negative fashion, so that one experiences big deviations only in cases where the other one experiences small deviations. Now the expectation is just giving a probabilistic sense of this. It doesn't mean that every time that x experiences a big deviation, y will experience a small or a large deviation. But it means with what probability, when x is experiencing a deviation, will y experience a big one. If that probability is large, and if when x experiences small deviations, y also experiences small deviations, if that probability is large, then the expectation will yield a positive number, so that you see that these random variables are positively co-moving. Likewise, if negative deviations of x, if big ones coincide probabilistically with small ones for y, then you see negative co-movement of these random variables. So now, using the properties of expectations, we can show a result which is actually very similar to that we proved for variance. Let's begin by actually writing out the definition of covariance. That's equal to the expectation, and again I'm going to substitute the mu definition for each one of these. It's the expectation of deviations, and I'm going to call the mean of x mu x times the deviation of y from mu y. And I take the expectation of that product. Well, let's distribute. That's equal to the expectation of x y minus mu y x minus mu x y plus mu x mu y. Now we can carry the expectation through, so that we have expectation of xy minus, I'm going to pull the constant out, mu y, expectation of x, minus mu x times the expectation of y. And the final term is just a constant, so I don't need the expectation. Now it turns out this is mu x, and this is mu y. So this is all equal to expected value of x, y, minus mu y, mu x, minus mu x, mu y, plus mu x, mu y. Let's just cancel out these last two, and what do we have? We have expected value of x, y, and now I'm just going to substitute in for what mu x and mu y are. That's expected value of x, expected value of y. There's our proof. Now it turns out, recall, if we just say the covariance of x with itself, what is that equal to? Well, by that latter definition that we just used, that's equal to covariance of expectation of x times x minus expectation of x times expectation of x, right? And that is equal to expectation of x squared minus expectation of x quantity squared, which is the variance. And in fact, we previously proved this for the variance, but all we needed to do was first prove it for the covariance, generally for the covariance of x with some random variable y, to get to that expression, and then we could have specialized it to the substituting x for any random variable y to arrive at that expression.